Hi class, I hope you're all doing well. Welcome to the second half of lecture today. So this part of the lecture, we're going to talk about using light as a tool to look for exoplanets. And so some of you may have had glasses like the ones I'm wearing on before. They're often sold around 4th of July or around Christmas to wear to produce kind of sparkly spectrum effects around fireworks or lights or Christmas lights or anything that you're looking at. They're a very old tool in physics called diffraction gratings. The diffraction grating is a piece of thin, transparent material that has very small scratches, parallel scratches in it, and each of those scratches kind of acts like a miniature prism, so that when light passes through them, it produces a gigantic spectrum separation of color. And so this particular implementation is very useful in spectroscopy and very useful in designing instruments and very useful for doing things yourselves. It probably doesn't surprise you to know that I have a pair of these in my desk all the time, which is why I have some. You may have some laying around the house. If you do, you should certainly get them out. But let me see if we can do this here. I'm going to hold them up to the camera on my computer so that the computer is looking through it. And then I'm going to hold up a flashlight. Okay, so this is just an ordinary flashlight. Sorry, the green screen is kind of ducking out the yellow there. And if I turn it on, and then you look at the light, so you see down there kind of underneath the light, the rainbow spectrum. So the diffraction grating is taking the light from the flashlight and dividing it into its individual spectrum colors. Okay, so I have another one here. Let's see if we can get it to show up just a little bit better there. Okay, so here's another light. Okay, and so you can see there that line going across the side of my hoodie there. Okay, so you can see the blue, the green, the red, and then the blue again as it goes on. So diffraction gratings repeat the spectrum time and time again. So that's what you're seeing going on there. Okay, so if you do this for all kinds of lights around your house, particularly if you have old-fashioned incandescent lights, you will find that their spectrums are continuous. LEDs are getting better, they're a little bit continuous, but if you look at compact fluorescent lights, which many of you may have, okay, so you can see the spiral compact fluorescent bulb here, okay, the diffraction pattern for a compact fluorescent bulb is very distinct colors, okay, so not every color is present in the light that comes from a fluorescent light bulb. Okay, and that's because of the process by which we generate the light in the fluorescent bulb. There's a gas in there, that gas is activated, and the gas only gives off certain colors of light. And that's part of the story that we're going to talk about today because it's useful for us in studying astronomy. Okay, as well are diffraction things. So if you have can find a set of these, go ahead and play with them, enjoy yourselves. Let me know what sorts of cool things you see around your house that have different colors of light. Okay? Okay, so let me share some slides here. So we're going to talk about using light as a tool to find exoplanets, okay? So the basic story we're going to tell here is we're going to talk about spectroscopic lines and what they are. We're going to talk about how they can tell us about the composition of an object, and then we're going to talk about how those lines can shift around and how from that shifting around we can tell something about the motion, which is going to be one of the primary ways that we look for exoplanets. Okay, so the last time we talked about the fact that we could look for the planet directly. Okay, so we talked about direct imaging by covering up the star and then looking for the faint light of the planet nearby. What we're really talking about here is we're talking about looking at the light from the star, doing spectroscopy on the light from the star so that we can look for the effects the planet are having on the star. Okay, so this is the kind of second part of the story that we started at the beginning of lecture. So I'll remind you that we've talked about stellar spectra before. So this is the spectral sequence that Annie Jump Cannon reordered by spectral temperature over there on the right. You'll see the spectral names over there on the left. And as you can see, sloping from the hottest stars, where they're bluer, more purplish stars, all the way down to the coolest stars, which are the more reddish stars. Okay, so when you first saw this, we just talked about the general overall impression of where most of the color was saturated in these spectrums, what part of the spectrum was brightest. But what we didn't talk about is when you look at these spectra, they're not continuous smears of light. There are very distinct black and dark lines there in these individual spectra. Okay, so that's very easy to see with modern technology, but it wasn't always. In fact, this was only discovered in the 1800s, about the 1820s or so. And it's something that today is invaluable in astronomy. We exploit it in many ways, including the search for exoplanets. Okay, so let me show you this in great detail. So this is the Big Dipper. You can see it there at the top. And so this is right when it gets dark this time of year. It's kind of very close to overhead. And so if you can recognize the Big Dipper, you'll see it has a bowl and then a big handle. And so we can use the handle to find a nearby bright red star. Okay, and that star's name is Arcturus. So as we say, the mnemonic that we use when we're staring at the Big Dipper is we arc to Arcturus. We follow the arc of the handle across the sky, and the first bright red star we come to is the star Arcturus. Okay, so what I'm going to do is I'm going to show you the spectrum of the sun, and then I'm going to show you the spectrum of Arcturus. I'm going to show you them back to back so you can see what they look like. Okay, so this is the spectrum of the sun. So this is one of the highest resolution spectrums of the sun ever taken. If it was printed out, it would be something like 100 feet long or so. But it was taken explicitly to be able to show the rich diversity of black lines that you see in the spectrum. Okay, and we'll talk about what those are in a minute. What I want you to notice from this right now is some of them are narrow, some of them are wide, some of them are very fat, some are kind of hard to see, some are there in pairs or triplets or in groups, and so on. Okay, now I'm going to replace this, I'm going to exactly overlay it with the spectrum from Arcturus. So pick a favorite line that you're looking at, just stare at it, and then when I do the transition to the next slide, look at how that line changes. Okay, so for many of these lines, some of them disappeared, some of them got stronger, some new ones appeared, okay? So the spectrums of the sun and Arcturus are different from each other. And if I just swap back and forth between them, you can see that they are very distinctly different. And that has to do with the fact that the stars are different ages, and as we'll discuss in a moment, it has to do with their overall chemical composition, okay? Now, the person who discovered the lines in the sun was a German named Fraunhofer. And so these lines are sometimes called Fraunhofer lines. And when you come back to Chicago, if you get a chance and the museums are back open again, you should go down to the Adler Planetarium. And this is Fraunhofer's original sketch of all the dark lines that he could see in the solar spectrum. Okay, so Fraunhofer made this discovery in the early 1800s before we had photography. And so the way he had to measure all of the lines in the solar spectrum, those ones that you and I are looking at here in these spectrums, the way he had to do it is he had a device called a spectroscope, which doesn't work that dissimilarly from the spectral glasses that we put on. And he had to look at where each of the lines was, measure visually the distance between them, and then record them here in this extremely long chart. He saw 474 individual lines. There are many more than that we know today. Our telescopes are much better than Fraunhofer's, but he was the first person to characterize these in the sun. Okay, and so the question is, well, what are these things? Okay, so this was a mystery that began a little bit before Fraunhofer, about 10 years before, by a guy named what was his name? Wollaston. So Wollaston was the first person who discovered that when you look at a candle flame through a spectrum, you see individual lines. And Fraunhofer discovered them in the sun, and so the scientific community got swept up in trying to understand what are all these lines. What we eventually discovered is that all of these lines are the individual fingerprints of the chemical elements that are on the periodic table. Okay, so every element, so this is every element on the periodic table here, every element has a unique set of lines, a unique set of colors of light that it gives off. And by the converse, this is what's going on in the sun. It has a unique set of lines, a unique set of colors of light that it absorbs, that it can remove from a spectrum. And so the explanation for what are the dark lines in the spectra that we've been looking at is they are the signatures of the chemical elements that can be found in the atmospheres of the stars. Okay, so one of the things that we do in astronomy with these lines is we measure the chemical composition and the abundance of the chemicals, in this case, as we're talking about right now, in the atmospheres of stars. But this is exactly how we know what the chemical composition of asteroids are and comets are, and as it turns out, of the exoplanets are going to be, because we can measure the light that we get from those worlds. We can tease the light apart into the individual fingerprints, into the individual signatures, and tell you what the chemical composition of those places are. Because every chemical element has a unique fingerprint that marks its presence. Okay? But how are we going to use this? So we will use this to characterize exoplanet atmospheres. And we'll talk about this a little bit more in a couple of lectures where we both want to know what is the content of the atmospheres. But the other thing that we're looking for is we're looking for something called biosignatures. We're looking for gases and elements given off due to life processes like carbon dioxide that we've talked about in the past. Okay, but we'll definitely use this same technology for exoplanets. But today we're talking about what do we do to discover exoplanets? What can we do with light so that we can find out that exoplanets are actually really out there? Okay, so the way we do that is we look at the actual location of the lines in the spectrum. Okay, so I've drawn this here as a bright line spectrum because it's a little bit easier demonstration to do with a bright line spectrum, but it applies equally well to the dark line spectrum that we see in the stars. Okay, so if the star is sitting still, and I measure its spectrum, say I'm measuring the helium lines in the star, I will get some set of lines just like the ones that I show you here, okay? And they will match the lines of helium that you and I can measure if we just went to the physics lab here in the labs here at Northwestern. Okay, so this is in fact a lab that we make you do if you take introductory physics. We give you a tube full of helium, we have you look at it through a spectral diffraction grating and just mark where all the lines are. Okay, so we can do that. That's called the lab measurement of the helium lines. But if the star is moving towards you, all of those lines shift towards the blue end of the spectrum, and they all shift by the same amount. So we call that a blue shift. And if the star is moving towards us, this is what the helium spectrum looks like. Okay, it's still exactly the same set of lines that helium had, but all of them are moved over to the blue end of the spectrum a little bit. Okay, so the way we identify helium in a star is we go look for this particular pattern of one big space, one big space, two little space, one little space, one big space, and then there's a purple line. Okay, so we look for that pattern at these exact separations. We don't see it at the helium pattern that we see in the lab, but if I scoot it over just a little bit and all the lines match up, then I know I have helium. Okay? The exact same thing happens if the star is moving away from you. And if the star is moving away from you, all those lines that we see in the lab shift not to the blue, but they shift to the red. Okay, and so it's the same set of lines, same relationship, big space, small space, medium space, big space, just every line is shifted a little bit to the red. So we call these blue shifts and red shifts. And you'll hear astronomers talk about this all the time. What's the blue shift of that star? What's the red shift of that galaxy? Because we use blue shifts and red shifts to tell whether or not something's moving towards us or whether or not something's moving away from us. And the important point here is based on how much the lines move, we can tell you exactly how fast the object is moving, whether it's a star, planet, galaxy, whatever we're measuring the red shift or blue shift in. I can tell you how fast it's going by measuring how far those little lines shift. Okay? So, what use is this with exoplanets? Well, the use of this in exoplanets is you'll remember when we talked about gravity a couple weeks ago, we said every object exerts gravitational influence on every other object. And you and I feel like we never pull on the Earth only pulls on us because the Earth is enormous compared to us. Well, as it turns out, the stars pull on the planets, but the planets also pull on the stars. And if the planet is big enough, our technology today is good enough to tell that the planet is pulling on the star. Okay, so imagine this situation here where you have a planet that's orbiting the star. And the planet is constantly pulling the star towards it, and the star is constantly pulling the planet towards it. But you and I are just going to point our telescope and we're going to measure the light from the stars. And so anytime the planet is coming towards us in this image, then gravity forces the star to move in the opposite direction, moving away from us. And you should see a redshift. And eventually the planet in its orbit is moving away from us, and gravity forces the star to move towards us. And so we see a blue shift. And so one of the things we look for to identify planets using light is we look for alternating redshift and blue shift. Okay, so this is called radial velocity technique. We'll talk about this a little bit more next lecture. And it's one of the primary methods by which we first started discovering exoplanets. Okay, so I'll play this movie. So the star is going away from us when the planet's coming towards us, and you see a redshift. When the planet's going away from us, the star is coming towards us, and you see a blue shift. And then it just oscillates back and forth. Red shift. And then when the planet reaches the other side of its orbit, blue shift. Star is coming towards us. Planet reaches the other side. Whoops, movie ended. Okay, other side of the orbit, when the planet is coming towards us, we'll get the red shift of the star because it's going away, and on and on and on. Okay, so this is the so-called radial velocity technique, and it completely depends on your ability to be able to measure the spectrum, not of the planet, but the spectrum of the star, because the planet's constantly tugging the star back and forth, causing that blue shift and red shift in the light. Okay? Okay, so that's all I'm going to say today for that part of the lecture. So this has been about how we use light, and in particular the spectral properties of light, to detect the presence of a planet around a star. Next class, we'll talk about all the different techniques. There's like 5 different techniques that we use to measure exoplanets, and then we'll talk about the exoplanet catalogs that we've had. Okay, so I hope you're all doing well. Please be safe and take care of yourselves, and we'll talk to you again soon.